Okay, so this PowerPoint is all about Coulombic attraction. Now, that's kind of a crazy word. Coulombic attraction is essentially the attraction between oppositely charged particles. Okay, so we're specifically talking in an atom. And when we're looking at which particles are oppositely charged, we have the protons, which are positively charged and in the nucleus, and then we have the electrons, which are negatively charged in the electron cloud. When we're looking at Coulombic attraction, we're specifically talking about the outermost electrons, or the valence electrons. Those are the electrons in the outermost ring of our electron cloud. And what Coulombic attraction really allows us to do is, if we understand this, we can explain all of those trends that we see, or all those patterns that we see on the periodic table. So, Coulombic attraction, as I said, is the attraction between oppositely charged particles, the protons and the electrons. So what we're looking at is what happens as we go down a group or across a period with the Coulombic attraction, because our number of protons and electrons are changing, but also the distance between them is changing as we add more and more rings. So as the distance between the protons and electrons increases, the force of attraction decreases. So think of it kind of like a magnet. If we have two magnets that are really close together, we're gonna really feel that pull on the force. But as we move those magnets further and further apart, the pull that is felt is less and less. Okay, and that is because that distance is increasing. So when we go down a group, we are adding more energy levels, which means that distance is increasing, so our attraction is less. So something like lithium at the top of the periodic table, or at the top of that group 1, is going to have a really strong Coulombic attraction, whereas potassium, only 2 elements below lithium, is going to have a smaller Coulombic attraction, just simply because we have more distance. Okay. As we move across the periodic table, then, the distance stays the same, right? Those outer electrons are in the same energy level. But what we're doing is adding more electrons to that energy level and more protons in the middle. Essentially, we're making that magnet stronger. So when we go from left to right across the periodic table, we are increasing the strength of the magnet, which makes the Coulombic attraction increase. Okay, if we're comparing the two things, so distance to strength, distance to the nucleus is more important than the strength of that pull, than the number of protons in the nucleus for determining an attractive force. So if we have something that has 2 electrons in the outer ring, but the distance is only 2 rings away, that's going to still have a stronger pull than something that maybe has 3 rings away but 2 electrons. Okay, so in summary, right here in the middle, more energy levels, the valence electrons are further from the nucleus, which means we have less attractive force, less Coulombic attraction. When we have more energy levels, there's also more electron shielding, so there's more stuff for that force to go through. When we're in the same period, though, the number of energy levels is the same and the electron shielding is the same. So there are those more protons make there be more attraction. Okay, so this is kind of what you need to know about Coulombic attraction. Now we're going to look at how does that apply to our 3 different trends. So atomic radius, we can think of that as the size of the atom. You should have looked at that in the last set of notes. This decreases as we go across from left to right. Why? This would be the part that's new, what you're using Coulombic attraction to explain. Remember, as we go from left to right, our shielding is the same, the distance is the same, but we have more protons and neutrons, more protons and electrons, which means that that pull is greater. So our distance from the nucleus to the outer ring is the same. As we're moving from left to right, there's more protons and more electrons in equal proportion. This is kind of your key. You have a stronger magnet, which makes that pull smaller. Because the nucleus has more pull over the same distance, the radius shrinks because there's more Coulombic attraction. Now, as we go down the periodic table, our atomic radius is increasing. Why? The distance from the nucleus to the outer ring is larger, okay? So we add an extra ring or an extra layer. Yes, there are more protons and more electrons in equal proportion, but that more pull is spread over a greater distance. And remember, distance is more important than strength. So the greater distance equals less Coulombic attraction, which means that we have an increase in our radius as we move down. Now, ionization energy. This can be thought of as how much energy it takes to remove an outer electron, okay? So we can kind of think about it as how much does that nucleus really want the electrons it has, and then therefore how much does it really want the any extra electrons. Oh, sorry. Sorry, I said that wrong. It is how badly the nucleus wants the electrons it has and how tightly it's hanging on to them, okay? So if a nucleus is holding on to the electrons that it has really tightly, meaning the Coulombic attraction is really high, it's going to take a lot of work or a lot of energy for something else to remove one of those electrons, okay? So when there's greater Coulombic attraction, such as when we move from left to right across the periodic table, the ionization energy is greater because it's harder to remove that electron. Those elements really are hanging on to their electrons tightly. When there's less Coulombic attraction going down the periodic table, the ionization energy is smaller. It's easier to remove an electron. Remember, we saw as we move down the periodic table, there is less and less Coulombic attraction. Now, last one, electronegativity. This is the one. How good is an element at attracting extra electrons? Okay, that's what I was starting to explain with ionization energy. Electronegativity is the opposite of ionization energy, okay? It's not just how tightly are we hanging on to the electrons we already have, it's how good are we going to be at pulling in an extra electron, okay? So if we're not holding on to the things we have, we're probably not going to be very good at pulling in something extra. Think of it like if you can't keep track of your stuff, you probably shouldn't add more stuff to keep track of, okay? So when there's greater Coulombic attraction, when we move from left to right across the periodic table, the electronegativity increases. That's because they are better at attracting electrons. Remember that element, that atom, is really good at hanging on to the stuff it already has. It doesn't want to let it go, and it is so good at that it's willing to take on some extra electrons. Now, when there's less Coulombic attraction, such as when we go down the periodic table, the electronegativity decreases. It doesn't want to pull on any extra electrons. It can barely handle the one it's got. So it is not going to try to pull in any extra electrons because it doesn't feel the need to have any more. Okay. Now, electronegativity is a little weird. It's not a measured value. It's just a scale, like a rating scale. So it is measured in what's called Pauling units, and that's just named after the guy who came up with the idea. And the greatest number is 4, and the lowest then is 0. So the closer we get to 4, the stronger that Coulombic attraction is, the better they are at attracting extra electrons. Okay, Coulombic attraction can be used to explain the trends on the periodic table. So it's great that you might have memorized those trends from the last PowerPoint, but in order to really, really be able to explain them, we want you to be able to explain Coulombic attraction. Okay. Now, if you have any questions about this, make sure you're asking your teacher. Otherwise, go ahead and get started on those notes pieces or on those practice activities.